Hello, welcome to this video. We're going to go through compound interest equations and something called continuous compound interest. So what we'll do is kind of just start talking about different types of interest accounts. We'll use Desmos.com a little bit to solve some of these, and then eventually we'll get into the continuous compound, which is a different formula. So two different formulas today. The first one, continuous compound interest, deals with when interest is compounded multiple times throughout a year. So this is the same formula that we could use if interest was compounded once a year. So if interest was compounded once a year, what we would do is put the value of 1 in for the letter n. So n represents the number of times something is compounded per year. So if something is compounded semi-annually, we would use an n value of 2. If something was compounded quarterly, we'd use an n value of 4. Monthly would be 12. I could say daily, and you would put 365. Again, representing how many times you're really adding interest to that account per 1 year. So if you were only adding interest annually, meaning once a year, you would basically just put a value of 1 in for n, and it would turn the equation into 1 plus r divided by n, well, that's just r, and then 1 times t is just t. And this is the same equation that we had previously used for annual interest compounding. So what I'm going to do is just kind of model a situation where we're going to use an investment of $10,000, and that's our p-value, and we're going to use a 4% interest rate. So I'm going to set this formula up in Desmos and show you a way to calculate a table really fast. And the formula we're going to end up using then, is y equals, and for our p-value, we'll use 10,000. Wow, that's 1,000. There's 10,000. 1 plus, and then it's the r value of 4%, so 0.04. And then I'm going to just demonstrate first with using the semi-annual, which is at 2, and then raise that to the power of 2t. So this is the first equation that we're going to put into Desmos and create a table of values. And then I can even kind of just zoom out on a graph and show you what this graph looks like for this. And then we'll change the n value to 4, and then we'll change the n value finally to 12. And then we'll kind of see a relationship grow between those values. So I'm going to just bounce over here and type in the equation. So y equals, and it was 10,000, and then 1 plus, and then in order to get this in, you're going to do 0.04. If I hit the little slash for divided by, I can enter in that number of times that we're compounding per year, so I'll put 2 there. If I hit the right arrow on my keyboard, I can move over and I'll put a parenthesis there. So holding down shift and then 0 gives me that right parenthesis. Now to get an exponent, the shortcut is to hold down shift and press the number 6. And that'll bring us up for an exponent where I can just put 2t. You could use x, t, doesn't even matter. So this is our equation that we have. And if I want to just show you what it looks like on a graph, I can hit this little wrench up top right, which tells me my graph settings. And I'm going to change my graph window to go from an x value of 0 to an x value of 30. And I'm going to count by 5s. So that would represent our x values of 0 to 30 years, counting every 5 years. My y values, I know that I'm not going to have any lower than 10,000 in the account, but just so I can see the y-intercept show up on there, I am just going to put 5,000. And then I'm going to go up to a value of, let's just say 50,000. And I can count by 10,000. Alright, and then if I hit this little wrench thing, that'll go away. So if I were to like zoom out or anything like that, it's automatically just going to change all of these values for us, but we'll still have a pretty good picture of what's going on in this graph. So if I click any point on this, it'll tell me the x-coordinate representing how many years have gone by, and the y-coordinate would tell you the amount that's in that bank account. So I can see the balance obviously increasing, and it's non-linear. So we can see that it's not going up at a constant rate of change, and it gives us that slight curve. And the curve ends up getting steeper and steeper as I move to the right. So the further the time goes on, the more and more is added to this account. If I want to figure out these amounts, so from the table of values then, so if I bounce back to here, we want to fill in the values for 1, 5, 10, 20, and then all the way out to 50. What I can do is hit this little edit list up top, and then right here it's got a conversion to a table. So what I can do, instead of using these values, because that would represent -2 years, -1 year, 0 year, what I'm going to do is enter in our values of 1, and then I can hit down arrow, 5, down arrow, 10, 20, and 50. And that's going to give us our values. And if you're copying these into the table, you can just round to the nearest dollar. You could round to dollars and cents, so that would be your nearest hundredth. Pretty flexible on what we're looking at. Again, the idea is that we're just kind of seeing that this account goes from $10,000, and after 50 years, we're up to $72,446. So, like I said, what we're going to do is change the equation slightly. So these are the values for semi-annual. Now what we're going to see is the more times that you add interest per year, the more that balance is going to reach. So I'm going to click here where it says 2, and to make the quarterly, I'm going to switch this value to 4, and then I'm also going to go up to my exponent and switch that 2 to a 4 as well. And we can see those same points now from the table, the 1, 5, 10, 20, and 50, but now these dollar amounts increase. So I'm still going from this 10,000, instead of it being 404, this balance after 1 year is 406. And instead of my value at 50 years being 72,446, I'm now up to 73,160. So the curve got a little bit steeper then by compounding that interest. Notice I didn't change the initial amount and I didn't change the interest rate. We just changed how many more times a year I was adding interest. So again, those 5 values you can take down. The last one we're going to go through is changing that denominator to 12. Again, that n value, how many times we're adding interest per year. So it changes the denominator and then the value that's in front of t. And again, that represents monthly. So now we're adding interest every month on this bank account. And now that value at 50 is up to 73,645. Okay, so again, that's going to represent, obviously we can see this relationship that the more times I compound it, the higher that value is going to be. So you can take those 5 values down, and really what we're just looking at is that relationship that the more times I add interest to this bank account, the more my total is going to be. Just for funsies, what I'm going to do is click the bottom here, and I'm going to change this to 365. So this would be if I were to add interest to this account every day, and now we're up to 73,882. So a couple hundred more dollars then. But what we'll eventually get into is, what if I really make this number a bunch? Let's say like 5,000. Eventually what we're going to see is we're going to hit a point where it really doesn't change much, and we can already see that when I had 365 in there, we were in the 73,800s. Now we're kind of getting to a point where it looks like I'm not adding much more, and we'll get into that towards the end of this video. So the next question, a little bit more straightforward. How long is it going to take this just a new investment, a $5,000 investment at a 5.5% quarterly compounded interest account to reach 8,000? So what we're going to do for this problem, I'm going to have my y equals, actually before I even jump into the equation, let's identify what we have. I know my principal amount, my initial amount is $5,000. I know that my interest rate is 5.5%, which as a decimal is 0.055, and that would just be sliding the decimal over 2 spots, indicating that we're just dividing by 100. And then it says that we are compounding this quarterly, so quarters, like 4 quarters in a dollar. So quarterly means my n value is 4. And what we don't know is t. What we want to actually find is t. So what we're going to do then is write out our equation, y equals, and it's 5,000 for the p-value, 1 plus an r over n, so 0.055, over my n value of 4 to the power of 4t. And that's what we're going to put in for one of our equations. So I'm going to put a little 1 next to this, y1, because if we were to use a graphing calculator, we would have y1, y2, y3, and all of our equations in there. What I'm going to do is take 8,000, and we're going to substitute that in for our second equation. So these 2 equations are what I'm going to put into Desmos, and we're going to just look for an intersection of them. So I'm going to bounce back to this, click the little x, and we're going to type in that first equation, y equals 5,000, to open a parenthesis is shift in the number 9, and then 1, and then to get a plus sign I can do shift, and then right there's by the backspace or by the delete key there's a plus equal sign key, and then type in 0.055 divided by, in this case it's 4 for quarterly. If I hit the right arrow, and then it's shift and 0 to get the parenthesis on there, and shift 6 was the exponent. So 4, and then we can use x or t, doesn't matter. And then in for y2, I'm going to put y equals 8,000. Alright, and what I can do is just zoom down. Again, I'm going to emphasize the use of a window here. If I hit this little wrench, and I made my x values go from 0, and let's just go to 15, counting by 2's. And I'm going to make my y values go from 0 to 10,000, counting by, let's just do 2,000. So what I can see, again, if I had my y value starting at 0, you can see the y-intercept is it's going to be 5,000, represent the starting balance of this bank account. What we want to look at is this intersection of the two, the line and the curve. So I can see that at 8.604, and that's years, so at 8.6 years, and we're going to find out what that is, the balance of the account will be 8,000. So the question says we want to round this to the nearest month. So I know 8 years is the 8, but 0.604. So what I'm going to do is get my calculator open, and if I want to know what 0.604 is, I can just take that 0.604, which was the leftover part of the decimal, and I can multiply that by 12, because that's how many months are in a year. And I get 7.248. So I'm just going to round that to 7. I'll round down to 7. So it indicates that it would take roughly 8 years and 7 months for that account to reach 8,000. And that would be our answer. So t equals, and it was 8 point, I forgot what the original amount was already. 604. So 8.604, which ends up basically being 8 years, and then that 0.604 was 7 months. Alright, so that is one of the cases where instead of the problem asking, hey, what's the balance after like 5 years or 6 years, in this case I want to know when. So since I wanted to solve for time, I needed to find that intersection of the curve and the line. Next problem is going to just take a look at a side-by-side between two different accounts. So I've got $12,500 deposited in one account that's got 4.8% interest, and we want to know how much more will be in that account if the interest is compounded monthly instead of annually. So monthly meaning 12 times a year, annually just meaning once a year. So n equals 12 versus n equals 1. So with this one, we don't even need the to use Desmos. I know that my principal value is 12,500. We know that our interest rate is 4.8%, which as a decimal is 0.048. And we know the t value is 10 years. So what I'm really going to do is kind of just make a little side-by-side between using n equals 12 and n equals 1 for our equations. So I'm going to go ahead and for n equals 12, start off by saying y equals, and we take that principal value of 12,500, and then I do 1 plus the r value of 0.048 over the n value of 12 to the power of 12 times 10. And I'll demonstrate how to do this in the calculator. So what I would do is type in 12,500, and then I can open a parenthesis here and do 1 plus, and then with a newer operating system, it's nice. This next part, we used to have to be able to put it in parentheses, the 0.048 over 12. What I can do is hit alpha and then y equals, and it's going to allow me to enter in a fraction. So this is where I'll put in my 0.048 over 12. Again, representing that that's monthly. If I hit the right arrow, I can close that off and then do this to the power of 12 times 10, which I can just enter like this. I could do 12 with the 10 in parentheses. Doesn't matter. At the end of the day, there's our balance, and I'm just going to give it in dollars and cents. So I end up with $20,181, and then that would round to 60 cents. So that's for the account that was compounded monthly, versus what if it's just compounded? What if I'm just adding interest once a year? Well, that would be y equals 12,500, and then that would be 1 plus 0.048 over 1 to the power of 1 times 10. What I want to emphasize that this is really just the original equation that we had done that deals with exponential growth, where I just have really 1 plus, and we know that 0.048 is just that r value. That could go here, and then 1 times 10 is just 10. So if we type this into the calculator, I'm going to end up with a balance of 19,000, so it's less, $976.66. So the question asks how much more would be in the account if it were compounded monthly rather than annually, and it is not much more. To go from one account to the other, or just to find the difference of the two, I would just subtract them. So taking my 20,181.6 and subtracting the 19,976.66, and that gives me a difference of $204.94. So over 10 years, adding that interest, compounding that interest monthly instead of just once a year would give you the benefit of having $204.94 more. And then we get to the last equation, which is slightly different. It's got this letter E in it instead of having all the parentheses and stuff. And what E means is that we are really compounding this an infinite number of times in a year. So I'll draw back, going back to the first part of this video, I had said, hey, what if we compounded that interest daily, 365 times? What if I did it 5,000 times a year? What if I compounded interest 100,000 times a year, or 1,000,000 times a year? Eventually, it seems like you would keep getting more and more and more, but eventually we get this amount, or this variable here, E, which just stands for the fact that we are always adding interest to this account. So I'm going to model this the same way that I did the others. I'm just going to start off by writing out what we know. It says that I've got a $20,000 investment. We want to know how much it's going to be worth in 5 years, so T is 5. And then my interest rate is 0.039, so a 3.9% interest rate, so R of 0.039. So this formula, there is no N. The idea of using the letter E represents how many times we are compounding this. And again, the idea is that it's continuously being compounded. So I write this as 20,000 times E to the 0.039, and then put 5 in for T. So all I'm doing is substituting our 3 values in, and then I'm going to go right to the calculator on this. So the only part with the calculator is finding out where E is, and it's hidden here in blue behind this LN button. So I'm going to type in my 20,000, and then I'm going to press second, and then the LN. So if I press second and then LN, I can get an E in there, and then I can just put in 0.039 times 5. And that's going to give me my balance. So my balance ends up being $24,306.22. So with this formula, again, it's different because we don't have the whole 1 plus R over N on the inside. We are assuming then that if we are compounding interest continuously, that we can just use this E value. So that's what E represents. So again, even if I were to try doing 20,000, and let's just say I did this interest 100 times in a year. So I would do 1 plus alpha y equals, and I could use that interest rate of 0.039 over, and let's just say again I did 100 times in a year. And I raise this to the power of 100 times 5, which would be 500. I get a balance that's pretty close to that. So again, the idea is even if I increase that one value, let's say I did this, I don't know, let's add a couple more zeros on there. So if I did 10,000, and then this would have to change to 50,000. So even if I compounded my interest 50,000 times in a year and I hit enter, I'm still going to get an amount. In this case, it's only 1 penny of a difference, but it is still going to be less than if I were to compound this continuously. So I could even boost this value up to like 1,000,000 times in a year, and eventually it would get closer and closer to just being the same thing as doing E. So again, E is what we're using for the continuous compound interest value.